Okay, I guess it's time to start. So first, it is our honor to have Professor Andreas Krause to give the one talk. Professor Andreas Krause is a professor of computer science at ETH Zurich, and he was also an assistant professor of computer science at Caltech, and he received his PhD in computer science from Carnegie Mellon University in 2008, and his diploma in computer science and mathematics from the Technical University of Munich in Germany in 2004. And he has received many different awards, including the ERC Starting Investigator and ERC Consolidator grants, the Deutsche Musters Canons Prize, and as a career award, the Okawa Foundation Research Grant, and ETH Golden Owl Teaching Award. And has also received the Test of Time Award from the ACM Special Interest Group in Knowledge Discovery and Data Mining, as well as the Test of Time Award from the ICML. So today it is our pleasure to have Professor Andreas Krause to give the talk here. Without further ado, let's welcome Professor Andreas Krause.
Thank you very much for this kind introduction. It's great to be back here at Caltech, if only for this virtual seminar. Good morning, everyone. Thanks a lot for joining. Today, I'd like to tell you about some work that we've been doing in our group on exploration and reinforcement learning, in particular looking at aspects related to safety and efficiency in this context. And this is joint work with a fantastic set of PhD students, postdocs, and senior collaborators, whom I'll acknowledge as we go along. Now, given this audience, I probably don't have to say too much about the reinforcement learning setup. Of course, it's a setting where there's an agent that's situated in some environment which it can affect by carrying out some actions, which might cause the environment to change its state and the agent to derive some reward from it. And of course, trouble is that our poor agent doesn't know how the world works. That it means it faces the dilemma of trading exploration, namely experimenting with different actions to learn about their consequences, and using what it learned, exploitation, in order to maximize its return. And of course, that problem has a rich history and sits exactly at the intersection of control and learning. It's been studied in machine learning for several decades, but of course also in control theory, using slightly different letters, different terms, and so on, going back in particular in the context to approximate dynamic programming, adaptive control, and so on. So I hope you don't mind if I stick with the RL notation for this talk, but of course these terms can translate. Now, given that rich history, we have still seen some pretty remarkable advances in recent years, in particular fueled through advances in deep learning and neural network representations. And you can't really give a talk about RL these days without acknowledging the amazing landmark victory that DeepMind has been achieving in the game of Go. That certainly has been a major challenge for AI research. That said, a lot of the advances that we've seen in RL in recent years really have been in settings where we basically have very accurate, if not perfect, computational models of the world. And of course, the best example of this are games. We know precisely how the Go board looks once we and our opponents have taken our moves. And that means that exploration is primarily a computational concern. And it's pretty amazing how far massive computes, along with clever algorithms, get you in solving these exploration problems in such very large spaces. However, if you think about deploying RL in high-stakes real-world applications like controlling, for example, renewable energy systems, scientific experiments, robotics applications, maybe even healthcare, then we rarely are in this luxurious position of having an accurate simulator. That means exploration really means collecting data, which certainly is expensive, but potentially really safety critical. So what we want to ask in this talk is basically, how should we design exploration strategies that are really data efficient and in particular that satisfy certain safety guarantees? So now I'd like to start with a particular setup where we started to explore this question, and that's in the context of safe Bayesian optimization that I'll introduce. And then we'll come back to a more control theoretic setup later on in this talk. And let me start with a concrete motivating application. So this is a collaboration that we have with the Paul Scherrer Institute. That's a federal research facility in Switzerland. And this is an instrument that they just finished, the Swissvale Electron Laser. It's a 700-meter long linear accelerator that generates X-ray pulses of extremely short duration, so femtosecond duration, 1/millionth of a billionth of a second at extremely high intensities. And so you can imagine, basically, you can use this basically to image extremely fast processes like molecules turning into each other in the context of chemical reactions. And of course, that has important applications from material science to drug discovery and other domains. It's also quite a complicated machine with many literally moving parts. So the beam properties are shaped by magnets that can be literally moved around, very subtly affecting these beam properties. And the beam properties also depend on environmental conditions like temperature, humidity, and need to be tuned with respect to application requirements. So it's not just that you set this machine once and use it, you have to constantly reconfigure it. And that's what we use reinforcement learning for. It's also a safety critical device. So you can't just arbitrarily experiment on this machine. If you're not careful, there can be a radiation damage, which basically might cause the magnets to be magnetized, the machine to be shut off, or possibly even really damaged. Now, fortunately, there's beam loss monitors installed in this machine, which can detect once we reach sort of critical levels. Now, how should we go about optimizing this performance? So on a high level, we can sort of think about this problem as basically one of optimizing the performance of some black box system, the free electron laser here, for example. And what we want to do is we want to sequentially inject a set of tuning parameters, call them theta t, that yield certain rewards, right? Maybe beam intensity is what we might care about here. In general, that's noisy. So we get noisy observations, which for most of this talk will be assuming sub-Gaussian. And also, in addition to the reward, we are going to observe how close we get to potentially violating any of those constraints. Now, at this point, I'd like to point out that while one can simulate, in principle, this laser, computational simulations are extremely expensive, extremely slow, and they also can't really capture the effect of current environmental conditions. So you really have to do these experiments live on the machine. Of course, the trouble is that your reward and constraints are unknown ahead of time. So given measurements you've taken, you need to close the loop to propose the next experiment that you're going to carry out. Of course, eventually our goal is to solve this constraint optimization problem, maximizing the performance subject to those constraints. But given these safety constraints, you need to make sure that every single solution, every single experiment we carry out along the way, every exploratory action is feasible. So essentially, we're facing a constraint optimization problem with an unknown objective under unknown constraints that we need to solve iteratively while maintaining feasibility of every single step along the way. So I should have convinced you that in general, this is a completely ill-posed problem. So we won't get anywhere unless we make certain assumptions. So the first assumption we'll make is that we know where to start. So we have initial feasible solution. In addition, we'll assume some sort of smoothness assumptions about this black box. And one very natural way of encoding prior assumptions is to take a Bayesian viewpoint. And that's exactly what's done in the field of Bayesian optimization, where we would take the reward function, in this case here also the constraint, and endow them with a probabilistic model. This then not only allows us to make predictions about actions we haven't tried yet, but also quantify the uncertainty in our prediction. And this uncertainty is crucial in navigating the exploitation dilemma, as well as reasoning about risk and safety. So most of you will probably be familiar with Gaussian processes. Just a quick primer. So essentially, so now, of course, at this point, we could use many different Bayesian models. So here, I'll focus for now on Gaussian processes, so de facto standard and Bayesian optimization. Later on, I'll tell you about results on using say Bayesian deep neural networks and so on in later parts of this talk. Okay, so essentially, we'll treat this unknown function as a sample path of realization out of many possible realizations of the stochastic process. As a Bayesian model, we can consider on basically condition on data to get a posterior distribution that contracts as we get more and more data. Now, a characterizing property of Gaussian processes that all finite marginals are Gaussian, and in fact, they're pairwise marginals characterized by the covariance function all smoothness properties of this stochastic process. So that's basically how we impose prior assumptions about that sort of model. Now, why is the uncertainty useful? Here's sort of an important cartoon picture to take into account. So imagine we've carried out a bunch of experiments shown by those pluses here. I hope you can see my pointer. And now we get a posterior prediction whose mean is given by this black line here. That's also the mode for a Gaussian, along with confidence bounds shown in green here. And if we can get ourselves into the position that the unknown function, this black box function, is really contained in these confidence bounds, then we can apply the following rationale. So in particular, we can look at the pessimistic estimate of the optimum, so this best lower bound. And now we can rest assured that the optimum of the function must be somewhere within this green subset of the domain, namely where the upper confidence bound exceeds this best lower bound. And that idea is really central in exploration and multi-arm bandits and reinforcement learning and so on. For example, justifies the optimism in the face of uncertainty principle that simply greedily maximizes the upper confidence bound as an index policy. Now, if you think about safety, then maybe being too optimistic is also not the right thing to do. But of course, one can apply a similar rationale to sort of think about constraints as well. Now, if this is our probabilistic model of the constraints, and we want to ensure that wherever we carry out our experiments, we exceed the safety threshold, then as long as our lower confidence bound here exceeds the safety threshold, we hopefully will be safe, right? As long as these confidence bounds are well calibrated. That means we can basically construct a conservative inner approximation of the feasible region using this statistical model. Now, a quick point that I want to make here is that what's crucial is that these confidence bounds will be well calibrated, and we'll get back to this issue quite a bit also at the end of this talk. So what this means that we really want the unknown function f to be contained in our confidence bounds, which for Gaussian process models are simply mean plus some multiple times the standard deviation. Now, of course, if you sort of truly believe that we have the prior from which the nature is drawn, then we can simply enumerate credible intervals by just trading mean and standard deviation by a certain amount and enumerate percentiles this way. The trouble is, of course, nature might not listen, right, and might not agree perfectly with our Bayesian model. So we really need to understand sort of how a mismatch between some arbitrary, potentially adversarially chosen function in nature agrees with our Bayesian model. But fortunately, it's possible to actually calibrate this Bayesian model in a way to yield valid frequentist confidence intervals. So you can scale these confidence intervals so that they hold universally across a set of functions we're considering, and as well as universally across points of the domain and time steps of the algorithm. And the way we need to calibrate them is to essentially take into account the complexity of the unknown function as measured with respect to the reproducing kernel Hilbert space norm associated with the covariance function that our Bayesian model is using, together with some notion of capacity, which essentially quantifies the effective degrees of freedom that our prior distribution has. I will not go into a lot of technical details here, so I could talk quite a bit about these things. What I want to point out is essentially that we have a fairly good understanding under what sort of circumstances it's possible to actually obtain these kind of confidence intervals, and as such, apply this kind of reasoning that we had in the previous slide. Okay, and so there's been quite a bit of research by us and others since this initial result, building on this idea. Okay, now one way to use these insights for Bayesian optimization is an algorithm that we call SafeOpt. That was actually developed in collaboration with folks at Caltech. So Yan Ansui is a Caltech alum, as well as Jewel Burdick at Caltech, and one of my former PhD students, Aki Scotto, was. And then extended later by a PhD student of mine, Felix Berkenkamp. And so here what we would do is we basically endow our reward and constraints with the Bayesian model, and use this kind of rationale we had before to construct our safe set, as well as a set of plausible optimizers shown in green. Now, it turns out that simply considering plausibly optimal solutions that are safe is not enough for exploration. So you can get stuck in local solutions because you don't explore the boundary enough. So you can modify the algorithm to also potentially consider experiments that plausibly allow you to infer additional actions to be safe. These are indicated in purple here. I'll spare you the formal definition. That's, of course, in the paper. And now among those relevant points that are safe as well as informative in this way, we would just pick out the experiment that provides as much information as possible. Eventually, we'll figure out that better solutions can be found in this part of the domain. And under the sort of assumptions that I've described to you before, that basically are sufficient for these confidence bounds to be well calibrated, we can guarantee both safety and completeness about the resulting algorithms. You can guarantee with arbitrarily high probability that it will never pick an unsafe decision, and one can get label complexity results on a number of experiments needed to find a good solution. Now, what good means depends a bit on the setup. In high dimensions, the best you can hope for are locally optimal solutions. For low dimensions, you can even get some global optimality guarantees. Now, that's the first version of that algorithm. Since then, quite a bit has happened, both in our group and others in the community. So for example, one issue with this first algorithm is that it tends to explore the boundary too much, which you can see on this little histogram here, because it really tries to sort of push and explore as much as possible. So one can fix this by doing this expansion to basically push the boundary in a more goal-oriented fashion. So that's an idea that we've described in the paper at NeurIPS a little while back, where one can use standard acquisition functions like the optimistic principle, for example, to propose a new experiment. As long as that is safe, we can just carry it out. If it's not, we can sort of try to plan a path towards it. So we can systematically carry out experiments that expand strategically our statistical safe set in order to make progress towards the experiment that we actually want to carry out. And then also, in order to really scale this to high dimensional systems and complex machines like the Swissvale Laser here, there's also techniques that we've been exploring that rely on repeatedly applying safe optimization on carefully chosen low dimensional subspaces, under which case one can still get sort of local optimality guarantees. So here I want to show you some results on the Swissvale Laser. So these are some experiments that my students, Johannes and Moimir, ran on the actual machine. So what they would do is they would start with the parameter settings that our expert collaborators manually found, and then they would detune the system to basically get much worse performance out of the laser. And then they would use different algorithms in order to try to recover. And one natural benchmark that is used in this domain are local search heuristics that don't have any safety guarantees, but often still work fairly well, like meld and meet, for example. But because of their local nature, they often actually get stuck in suboptimal solutions. In contrast, the algorithm that I've described to you before, basically a variant of this, typically outperforms these purely local methods, and oftentimes not only recovers the expert settings by the physicist, but sometimes even improves in terms of the parameter settings that are identified. Now, there's also quite a bit of other work and applications of safe Bayesian optimization that I want to point out in the area of advanced manufacturing, so the collaboration with John Ligger's group at ETH, as well as on using safe optimization in the context of optimizing the performance of building heating management systems. And I'd also like to point out a really exciting paper by Yanan Sui, one of the co-authors of the SafeOp paper, and his collaborators on medical applications using safe Bayesian optimization in actual clinical trials. That is an application that originally stimulated the research that was happening in this area. Now, one of the major shortcomings of this approach is really its black box nature, right? That essentially we treat, say, the laser or the objective that we would consider purely as a black box. And that's what we want to change. That is, we sort of want to improve. And one way to try to open up the black box is to sort of try to explicitly reason about dynamics of some underlying system. And that, of course, requires a much more sort of control theoretic setup. And I'd like to show you how some of these ideas that we've been exploring here can also be applied in order to safely learn about unknown nonlinear dynamical systems. So here we consider discrete time setup, right? We want to learn an unknown deterministic nonlinear system that maps state action pairs to next states. And this perspective very naturally allows you to incorporate certain types of prior information, like first principle models, where maybe F derives from some physics understanding of the underlying system. But that first principle model might not perfectly describe reality. So it's very natural to sort of try to, in a data-driven way, learn in a gray box fashion deviations from this first principle model. And of course, that's a classical idea that in the context of, say, Gaussian process models has, for example, been explored for Gaussian process dynamical models by the Empirical algorithm, by Rasmussen, also really exciting work by Claire Tomlin's group, Melanie Zeilinger's group, and so on. So that's a really nice way to sort of think about safe learning problems. And it also very naturally arises and has many motivations. So for example, if you think about training a model simulation, but then deploying it in real scenarios, you might have a simulator as your first principle model, but then essentially systematically learn the discrepancy of reality from the simulation by non-parametrically learning this disturbance. Or you might have a first principle model that, for example, well describes how a quadcopter works in midair, but fails to account for complex turbulent ground effects when hovering close to the ground, for example, that you can then try to learn from data. Okay, so I'll illustrate some of these ideas on kind of a reinforcement learning 101 hello world problem, the cart pole. So we want to get this cart pole to a target location, preferably without the pole falling to the ground. Okay, now what we want to do is we want to now explicitly reason about the dynamics of this of the system, the consequences of actions that we would apply. And so it's very natural to now basically use the confidence bounds and sort of the Gaussian process models, Bayesian models we've described to you before, in order to reason about plausible behaviors of the system for, say, any candidates of actions that you might apply, for example, in a receding horizon fashion. Right? So if you plan ahead for a couple of time steps, you would then forecast where you might plausibly end up under all systems that are supported by these non-parametric confidence bounds, right? And then hopefully try to pick actions that under all plausible realizations avoid unsafe states, right? When the pole is fallen to the ground, for example. Now, initially, of course, this will lead to very conservative behavior, right? As common in robust control, because you're just too unsure about the dynamics. But then as you move around in state space, collect more and more experience, one can refine these confidence estimates and basically enable much more performant and less conservative behavior. Okay, so that's sort of the high level idea. And now, of course, there's a lot of technical challenges to sort of make this work. So one is even how to get reliable multi-step ahead predictions, which you certainly would need for this sort of setup. And if you take models like Gaussian process models, the one step ahead predictions, they're nicely elliptic and Gaussian, right? So they're sort of well behaved. But if you iterate them through the nonlinear dynamics, simply, for example, just taking the mean estimate or the mode of the function leads to quite complex distortions that sort of look like this. Okay, so one natural question is sort of how can we get sort of tractable over approximations of these sort of effects? And that's what is a question that we looked at in a paper we published at CDC a little while back that basically systematically construct provably conservative elliptical over approximations, essentially, of this unknown dynamics that under the same regularity assumptions that we've discussed before are still guaranteed to be valid for all time steps with probability that you can specify ahead of time. Okay, and if you combine this with locally linear feedback controllers, these are sort of even reasonably tight and sort of can be applied to some at least sort of simpler systems. And I'll show you some examples of this. Now, of course, one problem is that even multi-step ahead predictions are not good enough. So if you think about safety, this is typically really requiring long-term properties, safety and stability properties. Okay, and so here's sort of a little cartoon example again in our cart pole setup. So if we plan only 2 time steps ahead, then we would conclude that sort of all these actions are still safe because sort of the next action would still be safe. But at this point, no matter what force we apply, that's within reasonable limits, we will not be able to put the pole into the upright position and eventually will crash. Okay, so we will not be able to return essentially to this to the safe region where we can still, for example, stabilize the cart pole in this example. Okay, and so it means that, and of course you can generalize this for arbitrary finite time ahead predictions. So a key question is how one can ensure and reason about long-term safety properties using these probabilistic models. And turns out that's actually possible, at least to some extent. So it's possible to use these one step ahead predictions even for certifying certain long-term safety properties. And that's what something that we've been looking in quite a bit and spending some time on. I'll illustrate one idea of how one can use this in the context of model predictive control. Okay, and so now here, the starting point will be the assumption that we not just have an unsafe set of states that we really want to avoid, but we also have a known set of safe states together with sort of a backup controller, a safe policy that has the property that is going to keep us within the safe set, right? So this safe set is going to be a forward invariant set under that policy, okay? And that sort of corresponds to this assumption of having a safe seed, sort of a starting point for safe exploration, which we of course need in this model-based setup just as well. And now if we start somewhere, for example, in this safe set, what we can do is now the following. So we can plan ahead two strategies in a receding horizon control fashion. So you can plan a performance trajectory, say over some number of steps ahead, that say seeks to trade exploration and exploitation, minimize stage costs to maximize our rewards, and so on. But at the same time, you're always keeping track of a fallback plan, a plan B. That's another trajectory which is guaranteed under all plausible realizations of our dynamics to take us back to the safe set. And now, crucially, we're going to tie those two together at the first action. So in the programming formulation, we'll require the first action of those two plans to agree. After the first action, of course, they can diverge. Okay, and now under that constraint, as long as these confidence bounds are well calibrated and valid, of course, no matter what happens after the first time step, we can simply replan and proceed. All right, so again, we plan our performance and safety trajectory, and this will allow us to always take us back to the safe set. Okay, and again, under the same regularity assumptions that we've discussed before, this now really allows to guarantee that we'll always be able to return back to the safe set, where we then have the backup controller which can keep us there. So we can really have a reason about long-term safety properties using this kind of idea. And here's an illustration on this card pull setup. So we compare an implementation of this strategy with prior work that also uses Gaussian process dynamics models to reason about essentially the non-parametric nonlinear dynamics, and that also uses ensures constraint satisfaction, in this case using chance constraint programming. However, it does not take the long-term planning into account. So only plans for finite number of ahead predictions. Okay, and so this method works really well in terms of minimizing the costs. So it finds an essentially optimal policy very quickly after about 10 episodes here with interacting with the system, and it very quickly is able to reduce the number of failures to a small level. However, since it only reasons about essentially these finite time ahead predictions and doesn't take the long-term essentially reachability properties into account, it actually does fail a bunch of times. And in contrast, the method that I've described to you before, it takes a little longer to find the essentially a policy of the same level. So about 15 episodes here as opposed to maybe 10, but it avoids failures completely along the way. Okay, so this is by basically taking into account this backup policy and by ensuring essentially this long-term safety property. Now, this is arguably a rather simple setup. And what we've been really focusing on recently is sort of scaling up these ideas and pushing them towards more complex high-dimensional systems using techniques from deep reinforcement learning. And that's what I'd like to tell you a bit about in the last part of this, in the second part of this talk here. Okay, and so in particular, we'll again look at an episodic setup where the agent essentially goes through a sequence of episodes, trials in the environment. Now, each episode, it has a current policy, a current controller that it will unroll to collect some data, to collect some experience. It will then go ahead together with all the data it's collected so far to refine its estimate of the dynamics model, F theta, and then uses this estimated model and the attached uncertainty in order to optimize its policy. Right now, the latter problem is itself a planning problem, right? A reinforcement learning problem, and one can use techniques from policy search, for example, in order to solve it. So the key question is basically how should we go about designing those experiments, how to roll out these policies in order to actually converge to a good policy. Okay, and to that end, it's one of the central principles that allows sort of principled exploration and reinforcement learning is really this optimism in the face of uncertainty principle. Right, so that we really briefly touched upon in the model free setup before, right, this Bayesian optimization setup before, but we can generalize these ideas to the episodic reinforcement learning setup. Now, what you would basically do is we would plan a policy pi that maximizes the return under the unknown dynamics But instead of considering arbitrary dynamics, we only consider plausible dynamics, namely those that are consistent with the statistical model that we've been estimating from past data. Okay, so that's an idea that has been analyzed in various settings, for example, the tabular or linear NDP setup. The idea, of course, goes back. Optimism has been extensively explored in reinforcement learning, but one paper that really analyzes the regrets of such episodic model-based reinforcement learning algorithm is the UCRL paper by Yak et al. From 2010. Okay, now the problem is that while this can be done in simple tabular MDPs, it's very difficult to scale to non-parametric and sort of non-linear settings, to basically using neural network controllers and dynamics models. And it's very difficult to implement. And the reason for that is that we have to solve this optimization problem over policies. And that's typically a non-convex problem. And then in turn, we have to optimize over the set of all statistically plausible dynamics models. And that's a very complicated constraint set. That's very difficult to describe in general. So this is really complicated optimization problem. That means that essentially the practice in deep RL is essentially certainty equivalent control. It's essentially a greedy method that essentially just conflates the uncertainty just in terms of the expectation. So what we're going to do is we're basically going to optimize our policy just with respect to the expected model based on past data. And that idea has been shown to work quite well in model-based reinforcement learning. So one seminal paper is the Pilko paper by Dijsselroth and Rasmussen from 2011, but also the PETS algorithm by Chu et al. That really showcases how one can use this under rich deep neural network ensemble models. And so one question that we've been exploring is how can one make use of confidence bounds and optimistic exploration really in complex setups like deep model-based reinforcement learning. And that's what I'd like to tell you a little bit about. In particular, what we found is that we can actually implement a reduction. So it turns out we can reduce this difficult optimization problem that's jointly over policies and over plausible models to sort of a reinforcement learning problem in standard form, where we essentially just perform certainty equivalent control, just maximizing greedy performance, but on a larger action space. Okay, and I'll explain more about that in just a second. And under the assumption that sort of the inner planning problem can be solved to optimality, this allows to obtain sublinear regret bounds, so really performance guarantees on essentially the complexity of solving that resulting optimization problem. So you can really guarantee convergence essentially to an optimal policy. But that is now a strategy where one can really use much more complex probabilistic models like Bayesian neural network models, for example, to reason about the uncertain dynamics. Okay, and I'd like to illustrate it on sort of this one-dimensional cartoon here to hopefully convey the gist of this algorithm. And it works as follows. So here the y-axis is the state space, just a one-dimensional state space. The x-axis is time. Okay, so we start at our starting state as 0, and we want to reach basically the sparse reward state over here. Now, what we would do is we, of course, optimize over policy, so mapping some states to actions, right? And our goal, of course, is to maximize the return of our policy pi. Now, our model allows us to predict where we might end up when carrying out a current policy pi under consideration in our starting state S0. But of course, there's some uncertainty attached, right? So that's basically the one-step confidence intervals that come out of this Bayesian model. And in general, we'll have to think about all plausible models, all plausible dynamics models here. So instead, the key idea behind our algorithm is to essentially hallucinate additional control. So basically allow the agent to control its luck. Okay, so we basically augment the agent's action space to choose where within the epistemic uncertainty, where within these one-step confidence intervals it wants to end up. That means we basically have just done nothing but increasing the action space, right? So instead of just optimizing all the actions, we now also get to optimize essentially over the realization of the uncertainty within these confidence intervals. Okay, and that is nothing but another state-dependent function, right? That's essentially the same kind of object that we anyways optimize over when doing policy search and reinforcement learning. Okay, and now by essentially combining the policy mapping and sort of the uncertainty mapping, we get an optimistic next state as S1 tilde. And then we can essentially unroll further, right? So by again following our policy, we get a distribution of our possible next states that we might end up with according to our epistemic uncertainty. And again, we ask the agent where it wants to end up. And this way construct this optimistic trajectory shown in this green dashed line that eventually really manages to find basically this sparse reward state. Okay, that's sort of the cartoon illustration, but one can basically essentially recast this as just an unconstrained standard policy search problem to which any standard algorithms that have been developed for model-free reinforcement learning and approximate dynamic programming can simply be applied to. So here's a little illustration on, again, sort of a hello world reinforcement learning example, the inverted pendulum, right? We want to swing up the pendulum into an upright position by applying some force. And what we're going to do is basically, we are going to look at the optimistic trajectory. So this is essentially the solution to the approximate dynamic programming problem, the policy search problem, purely on the estimated model, right? And its uncertainty. And here, basically, initially, since the agent doesn't really know about its consequences-free actions, there's sort of a lot of affordance it has in terms of the uncertainty. Okay, so it basically imagines it can immediately sort of swing up the pendulum by just pushing it in one direction. But then, of course, once the agent tries this in practice and deploys this policy, it quickly gets disappointed, right? So the pendulum doesn't actually swing up, but it visits some relevant states along the way, collects data, and of course, refines the probabilistic model with the uncertainty attached. Okay, now a little later, it has figured out that it's maybe a better idea to actually sort of swing back in one direction before you can swing up. And that's also what now the optimistic trajectory does. And when deploying this now, this still doesn't quite work because the model is not accurate enough. But of course, it now visits a larger, more relevant part of the state space. And after basically 5 episodes, it's actually able to swing up the pendulum. But since it hasn't collected data near the upright position, it overshoots slightly. But then basically after just 2 more episodes, essentially has found an optimal policy to this problem. Okay, so after a very small number of interactions with the real system, it basically has found a good policy. Again, that's a very simplistic example, but you can now really scale this to high dimensional systems. So I'll show you some experiments on the Mujoko benchmark suite. So this is basically a bunch of simulated robots that are often used as benchmark environments for deep reinforcement learning agents. And here the x-axis is the number of episodes, the amount of experience gathered, number of trials carried out on basically the in this case, of course, simulated robot. The y-axis is the return. And this red line here is basically the greedy strategy, right? The PETS algorithm, which is essentially the state of the art of this for this problem, that essentially does certainty equivalent control given the currently estimated model. Now, that indeed is able to improve the performance, but one can do better by sort of improving exploration. And one common exploration strategy that's also tractable to implement is Thompson sampling or posterior sampling, which basically samples from the posterior distribution of the plausible models. And this, in fact, leads to improved performance. But this optimistic strategy that I've described to you before still does quite a bit better, even on this basic setup. Now, that's still a fairly simple exploration problem, but even just greedy exploration basically solves the task. One can also make the exploration problem harder. And one way to make it harder is to increase the action penalty, to essentially have add a cost term that depends on the magnitude of the actions that are being applied. Okay, and this basically penalizes large actions. And as a consequence, random exploration, which is basically used by sort of the standard approaches, fails to visit relevant parts of the state space. And if you increase these action penalties more and more, at some point, the problem becomes too hard for these greedy strategies, and they don't work anymore. Whereas this optimistic strategy still finds very good solutions without any issues. Just to give you a bit of intuition, so if you don't have action penalties, essentially the simulator will tell you that sort of policies like this one here still move you forward, right? So by vigorously waving with the robot's extremities, you can still sort of by chance move the robot forward. But of course, if you sort of increase these action penalties, you really avoid larger controls, and that makes exploration much harder, but also in a way finds maybe more realistic policies might be more reasonable to deploy. So that's purely about improving efficiency of exploration. Similar ideas also generalize to robust reinforcement learning. That's sort of the analog to robust control in the RL literature, where one can now try to not just optimize expected performance of as we've described to you before with respect to the agent's policy under the unknown dynamics, but also consider some disturbances. We can model those again as sort of state-dependent policies that are now chosen by some adversary, and one sort of wants to solve that associated maximum optimization problem. And one question that really was not quite resolved is how to really properly do exploration for these types of robust reinforcement learning problems. And that's something that we've been looking into. And it turns out one can generalize these ideas that I've described to you to also solve basically these robust reinforcement learning problems now by combining optimistic exploration with sort of pessimistic exploration. So what we're going to do is we're going to look at two performance measures. So one performance measure that looks at sort of the optimistic model and one pessimistic performance that sort of looks at the worst possible plausible model that's supported by the probabilistic model that's been identified. And now the exploration strategy essentially goes as follows. So again, we proceed for a sequence of episodes. Every round, our agent acts optimistically according to this minimax optimization problem, but the opponent acts pessimistically, right? Or in some sense, optimistically with flipped sign in terms of sort of looking at the worst possible effect that it might have under all statistically plausible models. Then we would deploy these policies, collect data, and repeat again in this episodic fashion. And this now really works very well for these tasks that I've described to you before. So basically, here again, these are standard simulated robotics environments in this Mojoko benchmark suite that's often considered in deep reinforcement learning. And we compare basically the robust HUCR algorithm that I've described with a bunch of ablations that don't stress exploration as much. For example, just apply best response heuristics for the opponent. So certainly equivalent control for the opponent, for example, together with this non-robust policy that I've described to you before, as well as state-of-the-art algorithms that have been proposed exactly for that sort of setup. And in essentially all but one of these environments, this RHUCRL algorithm, in fact, gets the best worst case performance across these different environments. In some cases, really substantially outperforming prior work. And the summa here, it does maybe a little worse on average than some of these algorithms, but also there's fairly large error bars. It depends quite a bit on where you initialize the search. Okay, and maybe interestingly, even though we optimize sort of the robust, the worst case performance here, we can also, of course, look at the average case performance. We don't actually look at the worst case environment. We don't consider the disturbances. And sometimes it turns out that even when optimizing the worst case return, you can sometimes improve the average case return, which is somewhat counterintuitive because typically there's a trade-off between average case and worst case performance. But here, by considering essentially the worst case performance, that can really help exploration and sort of visit relevant parts of the search space in order to fit better models. And an example of this is here, this WOC environment, where really the RHUCR algorithm outperforms this HUCR algorithm, even though that optimizes average case performance and this one optimizes worst case performance. Okay, so I'm almost done. So in the last few minutes, I'd like to get to one really important issue that that's essentially central to most of the work that I've described in this talk, namely where do these probabilistic models come from? Okay, so the way I've described essentially the setup is from a Bayesian point of view, where I would manually specify a prior distribution over say the unknown function or the unknown dynamics and so on, and then basically apply Bayesian inference in order to construct these confidence estimates, obtain posterior distributions, and so on. And in some domains, this might be possible to really manually specify this, but in general, coming up really with a good prior is actually quite challenging. And so one natural question is, can we sort of learn a good prior directly from data? And that's something that we've been exploring, and it's a direction that I'm very excited about. And that we can look at from the perspective of meta-learning. So essentially, now imagine we already have collected experience from a bunch of related tasks that we can then use in order to obtain, basically via a meta-learning procedure that starts with some hyper prior to come up with the hyper posterior. So essentially a prior distribution that the base learner can now learn that's informed from past experience on related tasks that have been explored before. Okay, so that's the high level idea. And of course, there's many ways of how to instantiate in principle this idea. There's a lot of work on meta-learning. So in this work, we build on some beautiful work by Pentina and Lampert, as well as Emmett and Meyer, that motivates basically meta-learning from a packed Bayesian framework. So there's a way to sort of construct essentially these hyper priors and hyper posteriors by minimizing a certain kind of generalization bound across multiple tasks from packed Bayesian framework. Now, prior work has some considerable computational challenges. In particular, requires solving a complex nested optimization problem that's very hard to scale to modern deep reinforcement learning problems, for example. But this is still a great inspiration for this work. And so one result that we recently were basically able to obtain is by exploiting structural insights in this meta-learning setup, it's actually possible to construct in a way, in a certain way, an optimal hyperposterior. And it turns out that has very nice mathematical form, which is amenable to standard algorithms that we've been developing for approximate Bayesian inference. So I will not have time to go into these details in this talk here. I'd rather tell you a little bit about some results that can be obtained using this perspective, but I'd be happy to talk more later. And so here's some illustrations of this. So again, on a very simple stylized environment. So imagine we want to solve a collection of related regression problems. So these are very simple kind of one-dimensional regression problems. The related tasks are indicated by these different colors. Okay, so the blue points or the green points, the orange points, so they all correspond to different tasks. And here in the synthetic setup, these are just some sine curves, right? That have different phases, different frequencies, and so on, right? They're perturbed by some noise. And from each of these tasks, we actually observe very sparse data. So we only get to see 5 samples from each of these different tasks. Now, based on essentially this collection of training data sets, we can essentially apply this meta-learning strategy to now obtain a learned prior, like this hyperposterior, essentially, that we can now sample from. Okay, and on the right-hand side, you can see some sampled functions that are drawn from this hyperposterior that sort of capture this the structure in basically this regression problem, right? And the sinusoidal shape of these tasks, even though the model is not, of course, instructed to do something like this. And why is this useful? Well, if you're not using a well-specified prior, oftentimes you can get very bad predictions. So here's, for example, if you just use Bayesian neural network priors with putting Gaussian weights on the Gaussian priors on the weights of a neural network, it's sort of a standard thing to do, and you just condition on little data. Oftentimes, both the posterior mean predictions and the uncertainties are really quite poor, right? So here's some examples of these predictions. So not just the prediction error is quite large, but also the uncertainty is not very well calibrated. In contrast, if you essentially use this meta-learned prior from those tasks before, even when observing only very few examples from this related task, you do get quite meaningful uncertainty estimates and much better predictive performance. So here's some results on real data. So in this ICML paper that's coming up, so we report experiments on a data set for monitoring patients in an intensive care unit. So this is a time series forecasting problem where you basically learn an autoregressive model per patient. And so essentially here, each patient is a task. The goal is to sort of learn a personalized model for a given patient. And this other data set comes basically from the Swissvale free Electron laser that I've described to you before. And so here, essentially, each task corresponds to a tuning session, right? So I mentioned the performance of this laser depends very much on temperature, humidity, and these different environmental conditions. And so essentially, if you repeat the calibration procedure at multiple points in time, you sort of get different performance. Okay, and so we compare against a bunch of other meta-learning strategies as well as standard learners that just use a hand-designed prior with optimized parameters for those tasks. like a standard GP prior, for example, a Bayesian neural network prior. And in some cases, you can actually get quite substantial improvements in terms of the predictive performance, so the root mean squared error in terms of the prediction. But really, the most important part, if we want to use these models for decision making, is the calibration, right? It's sort of the uncertainty estimates. And so what you really want is that the models are well calibrated, right? That they might not give perfect predictions, but your confidence intervals better essentially cover the data you haven't seen, hopefully as tightly as possible, right? And so if you have poor calibration, you might get in situations like this, where essentially you rule out the true function based on your confidence intervals. And then, of course, all the reasoning that I've described to you before is moot. Okay, and so there's, of course, ways of quantifying this. So you can, for example, compare the empirical quantiles with the predicted quantiles that come out of these predictive models and try to align those as much as possible and quantify essentially the level of misalignment. Okay, and so here you also see quite substantial improvements in terms of the model calibration, at least for some of the tasks. So for PhysioNet, the improvements are not that large, but for the Swissvale data set, there's actually substantial improvements in terms of the model calibration that you can get from this meta-learned prior. And now here's some results that showcase essentially the utility of these learned prior distributions for an actual sequential decision-making task. And so here we'll come back to the Bayesian optimization setup that we explored at the beginning of this task. And in particular, we look at the Bayesian optimization task that actually is getting quite a lot of interest in the context of drug discovery and related domains. And in particular, we consider a data set where we want to identify a particular kind of peptide that maximizes binding affinity with respect to certain receptor molecules. So that's sort of a standard optimization problem that requires careful design of experiments, and where, of course, experiments are generally expensive to carry out, and Bayesian optimization is being explored as one of the techniques for really guiding this search. Okay, and now here in these settings, oftentimes you have related optimization problems as well. So in particular, you might not just have one receptor molecule, but multiple ones, and you need to find good sequences essentially for all these receptor molecules, all these target molecules. Okay, so instead of just applying one round of Bayesian optimization, of essentially experimenting with these different protein or enzyme candidates to try to find the one that maximizes binding affinity with respect to this target allele, now you actually want to share information across multiple related tasks that have been optimized for different receptor molecules in the training data. Okay, and that's, of course, now a meta-learning problem, right? One can sort of try to learn a good prior distribution that one can then use downstream in this Bayesian optimization task. And that really substantially can improve the experiment cost, essentially the sample efficiency of these exploration strategies. So here's an experiment where basically you compare against standard Bayesian optimization approaches, for example, based on GPs or based on Bayesian neural networks with different types of acquisition functions like optimistic exploration or Thompson sampling. So essentially, these are basically all based on hand-designed or hand-optimized priors for a given task. And the solid lines essentially come from applying the same exploration principles, but on these meta-learned prior distributions. And they quite substantially improve the sample complexity. So after very few experiments, you can actually find very good sequences. So that's quite exciting, and we're very actively exploring these kind of ideas for more general sequential decision tasks. So with that, I'm coming to the end of the talk. I think there is a lot of work still left to do if you want to lift the promise of reinforcement learning or data-driven control really to real-world applications like the ones that we've discussed here. So we talked about safety and data efficiency of exploration. There's many others, like really systematically dealing with partial observability, making optimal use of offline data that's related for these tasks, even thinking about what's the right kind of specifications of safety for these different systems, and so on. So I think it's a super exciting research area with many open questions. So with that, I'd like to conclude by thanking all the students, postdocs, and senior collaborators who contributed to this work. Thank you, all of you, for listening to this talk. Here's a few references if you want to read up on more detail on some of the work that I presented. and I'm very happy to take any questions that might arise. Thank you very much.
Thank you, Professor Krause, for this wonderful talk. There are some questions in the chat. The first question is from Daraya, which is about slide 27.
Yeah.
Can we go to that slide?
27 or 37?
27.
27, okay.
Yeah,
Let's see if I can. Oops. Sorry about this. Let me just go there quickly. Okay.
Yeah, so the question is that under the prior work graph, why does the failure number increase when the number of episodes go from 10 to 15?
Yeah, I mean, so this might be statistical fluctuations in this setup, right? So again, the policy minimizes essentially a violation of so essentially avoids failures within a finite number of ahead predictions that are looked at, right, for the horizon that's being considered in the setup. But there's no guarantee, right, that this will monotonically improve the performance of the trained policy.
Okay, sure, thanks. Yeah, the second question is from Charlotte Baden, and the question is that you refer to various regularity conditions required for the Gaussian process, probabilistic guarantees to hold. Does these sort of conditions hold for typical systems such like the card poll?
Yeah, so that's of course, I mean, very difficult to answer in general, and partly is also motivating the last part of this talk, right? To sort of give a more empirical answer to this. So now one aspect that I'd like to point out here is that what these regularity conditions essentially mean that the underlying function, let me try to go to that slide here, basically lives in a reproducing kernel Hilbert space that's associated with the covariance function that the Gaussian process prior is using. Okay, and so RKHSs are particular families of functions that are very well studied and that have understood mathematical properties. Now, to the extent that they really apply to a given system of interest, of course, that is very difficult to answer sort of in general. Now, then using commonly used kernels like, for example, the basis function kernel or Matern kernels and so on, they essentially impose a certain level of smoothness on the objective function, right? So the Gaussian kernel, for example, really requires that these unknown functions are extremely smooth, even analytic, so infinitely often differentiable. That maybe is too much to ask in practice. But for example, the RKHS associated with the Matern kernel, they control the level of mean square differentiability of the sample path. And the bandwidth parameter associated with these functions essentially controls the Lipschitz condition of these unknown functions, right? That's sort of important parameters like level of differentiability, Lipschitz conditions, and so on, that are much easier to understand and get sort of a handle on. But of course, beyond this, there's kernels designed for various different types of systems. So there's work, for example, exploring kernels specifically designed for certain types of dynamical systems that, of course, inject much more domain knowledge on the specific task. I think the main point here is really that this work sort of establishes a link between really the study of functions that can be captured by these reproducing kernel Hilbert spaces and the associated exploration, interactive learning problems.
Okay, yeah, thank you. And there's another question from Renyu Zhang, which is how to choose kernels for model-free Bayesian reinforcement learning. And specifically for continuous control, if the controllers or parameters are outside of the Bayesian region, then the infinite horizon cost will be infinity. Is there a way to use kernels to reflect the fact that some areas is infinity?
So, okay, I'm not exactly sure. So which part are you talking about?
So it's really, you can directly unmute yourself if you want to directly ask the question.
Yeah, but I think Professor Krause answer to the previous questions kind of answers my problem. Yeah, so basically I'm just wondering, say for the model-free algorithms like safe opt, it's kind of assuming that the F lies in some kind of a reproducing kernel Hilbert space.
Yeah.
But specifically for dynamical system, I guess the loss or the reward is going to blow up for regions that are unstable. And so in this sense, it kind of like the reproducing kernel Hilbert space is capturing more smoother, smoother function space instead of functions that have this kind of behavior. So I was wondering how to design new kernels, or is there ways to design new kernels to capture this kind of behavior?
Yeah, it's a great question. So there is some work that I briefly mentioned that is sort of exploring the design of kernels for particular types of dynamical systems. So Sebastian Trimpe in this group have been looking at these type of questions, for example. But in general, there are certainly open questions in this context. So you typically certainly would require additional constraints. I think one very interesting question is also that these types of assumptions are probably too much to impose on the entire domain, but maybe they're sort of sufficient if they hold locally, right? Because sort of the algorithm, if you think about safe opt, right, for example, this also doesn't necessarily need the model to be valid everywhere, right? It needs to be valid wherever it needs to be valid, right? That means essentially in the vicinity of where you've collected data, where you've been exploring, right? So you could imagine, for example, that there might be localized notions that essentially maybe only hold in parts of the domain, right? But still might be sufficient in order to guarantee the required properties. I think there's lots of interesting open questions in this context.
Yeah, that makes sense.
Does this answer your question? Okay, sure.
Thank you. There are two more quick questions. One is from Ahmad Gandhi Ahmad, which is is it possible to incorporate minimal effort control with control barrier functions given the learned unsafe set?
Yeah, so a great question. So I don't know. So it might very well be. So one thing that we've been looking at that goes a bit in that direction is essentially stability analysis. So using Lyapunov comparison functions, essentially. And so what one can do there is one can still use essentially these one-step ahead predictions and their associated confidence bounds to, for example, verify that all plausible models satisfy, say, this decrease condition of Lyapunov functions, right? It might be possible to generalize these ideas for arbitrary control barrier functions. I think it's an interesting question.
Okay, yeah, there's a last question, which is from Yingyin. On slide 26, can you give more intuition on the benefits of planning a performance strategy in addition to the safe strategy? How does it improve the performance and cost compared with the traditional robust MPC, which can also guarantee safety, but only consider a strategy that is both safe and optimizes performance?
Yeah, I mean, in some sense, this is a form of robust MPC, absolutely, right? I think the main point here is that the disturbance sets, they're data dependent, right? And so these confidence bounds essentially shrink as you gather more and more data. And given that fact, it makes sense to explore, right? To actually actively collect more data. And that's exactly one thing that the performance strategy can enable to do, right? So you can essentially, the performance strategy, and that's what we explore in this paper, can basically balance exploration and exploitation. So it can sort of minimize, for example, expected stage costs with some term that encourages sort of informative experiments, basically informative measurements. And that then basically sort of provides useful data that allow you to be less conservative in future experiments. I mean, that's essentially the high level motivation. And of course, here in the setting, so why you actually need sort of a performance and a safety trajectory. I mean, of course, oftentimes it's very easy to just satisfy safety on its own. That's not, of course, always the case, but sometimes, right? In this carpool example, you might just always stand still, but then you'll never be able to solve the task, right? Get maybe to a given goal location. And that's essentially, so what's happening in these experiments that I've showed, right? Where initially, basically, the card can only explore in a very local neighborhood by essentially relying on this balancing fallback controller that is guaranteeing to keep it in the safe set. But then as it gathers more and more data, it can essentially venture out and eventually successfully complete the task.
Okay, yeah, thank you. Yeah, I think so. I don't know what Ian thinks. Yeah. Yeah, anyways, thanks for the answers, and given the time, I guess we have to stop here. And yeah, let's thank again Professor Krause for giving this wonderful talk and answering all the questions. And next week we'll have Professor Miroslav Kristik from UCSD. Yeah. Thank you.